So notation-wise, derivatives are indicated by the little tick mark here. So something like y prime is the same as f prime of x, which is the same as dy dx. If you are taking the second derivative, it'll look like this. You'll have two tick marks here. And we did the notation for the second derivative. Third derivative would have three tick marks. If you get beyond three, they start using just parentheses with the number of derivatives that you are taking there. So you would continue doing that. Your position formula is your original. If S of t is your position formula, if you take the derivative of your position, it's going to give you the velocity. And then if you take the derivative of velocity, it's going to give you acceleration there. So those of you that are in physics, you've done a lot of position, velocity, acceleration sort of stuff. You guys are in algebra-based physics, so I'm not sure that they explain how those three relate to each other. But if you look at the formulas, if you start off with your position formula, if you take the derivative of it, it gives you your velocity formula. And if you take the derivative of that, it'll give you the acceleration formula, which for like gravity is just going to be 9.8. 32 if you're in feet, but in science you don't use feet. If we are taking a second derivative for this first example here, it's really straightforward. If you have a pretty simple derivative, it's not that bad at all. Let's see. So if we took first derivative here, we would just do 6x squared. Derivative of cosine is negative sign, so it'd be plus sine x. What's the derivative of natural log? 1 over x. And what's the derivative of e to the x? E to the x, so minus e to the x. So that would be our first derivative. Then we would just do that again. We would take the second derivative. So we get 12x. Derivative of sine is cosine x. What should I do with this 1 over x? What? We could do quotient rule, but there is an easier way because 1 over x is the same as x to the negative 1 power. So I would just use the power rule on that. So it'd be negative 1x to the negative 2 there. And then the derivative of e to the x would just be e to the x. They might write that negative x to the negative 2, they might write as 1 over x squared, but this is your second derivative. So finding higher order derivatives can be very simple if they give you simple equations, right? If it's just polynomials, if it's sine or cosine, it's not bad. Even e to the x is super easy because it's just itself over and over and over again. And then natural log is not too awful either. It's just going to be power rule there. Okay. Questions? All right, so here is some physics for you. Let's see. Anybody know how to say that? I meant to look it up. Burj Khalifa. Okay. So the Burj Khalifa, Burj was what I was not entirely sure about. So this is it still the tallest building? Still the tallest building in Dubai. It's huge. And it is 2,717 feet tall. And we are given a position equation that depicts the height in feet the ball is from the ground at time t in seconds, and it is modeled by this equation. So, if we were able to go to the top of this building and drop a ball from the very top here, then we could use this equation to compute the height of the ball. This is your pumpkin chunkin equation, if you did that long ago. And it is in feet and seconds rather than meters and seconds. So if you are in physics, you would see instead of -16 here, if you were doing meters and seconds, you would have, I think, -4.9, maybe, I think, for that. Yes, it would be 4.9, because whenever you took the derivative, that would give you 9.8. This is your initial height right here. This is your beginning velocity that you have here, but that's not necessary for you to know right now. So A says to compute the velocity of the ball at t equals 5. So if we are looking at the position formula here, this gives height, so that's our position. To find velocity, we're going to take the derivative. Okay? So if I take the derivative here, s prime of t, and what I like to do on these problems, I like to label velocity with a v, so it's velocity, but you need to show that you're taking the derivative. So I do s prime of t equals v of t, and so now I can call it v of t if I would like. And I'm going to just take the derivative here, so it's going to be -32t minus 10. And they asked for the velocity at 5, so I'm going to plug in 5. We'll say v of 5, or you can call it s prime of 5. Either is fine here because you labeled it both. So -32 times 5 minus 10. That is going to be -160 minus 10, -170 feet per second. Okay, why is it negative? It's going in the negative direction, down there, and velocity has direction. Okay. Next, they ask us to compute the acceleration of the ball. So if our velocity is -32t minus 10, we need to take the derivative of our velocity, or if we wanted to, we could call this s double prime. It's the second derivative of position, right? What is the derivative of the velocity? -32, right? So v prime of 5 is -32 feet per second squared. To think about if you're thinking about what you're doing here, like for this one over here, our graph was seconds on the x-axis, feet on the y-axis for position, right, for s of t. So when we take the derivative, it's changing y over changing x, which is feet over seconds, right? Over here for velocity, we have seconds here, and we've got feet per second. So whenever we do the derivative, it's going to be feet per second, and you can actually write it that way, feet per second, or that's like seconds over 1, so that'd be feet per second times 1 over seconds, which is feet per second squared. So that's where we get our units from. Also, your velocity is always going to be a distance over time, the acceleration is always going to be distance over time squared, whichever units you're using. Does it matter that it's at 5 for our acceleration? It is always the same. This is your acceleration due to gravity. It's going to be constant on Earth if you're ignoring air resistance, which you have to be here, right? So, so your acceleration due to gravity is negative 32 feet per second. So if we, it wouldn't matter if we were throwing something off of the top of this building, or if we threw something off of the, little ledge right here, it would fall at a rate of 32 feet per second squared, ignoring air resistance. Because air resistance complicates it way too much. All right, when will the ball hit the ground? So, what would we do? We would want to know, this is our position, which is our height, right? It's going to hit the ground whenever height is 0. So we can say 0 equals negative 16t squared minus 10t plus 2717. And so we would need to, I'm pretty sure that's not going to factor, so you could use quadratic formula for that. So it'd be opposite of b plus or minus square root b squared minus 4ac all over 2a, and this is calculator active. So we're going to get 100 minus 4 times negative 16 times 2717. So it's 10 plus or minus the square root of 17398 over negative 32. And you can do the whole thing at once. If you do, oh gosh. For the plus, you actually end up with a negative number. You get negative 13.3475. Does the negative number make sense for this particular equation? When we're asking when it's going to hit the ground. We wouldn't say a negative time, right? So you're going to do the minus, so you'll do 10 minus the square root of 173,988 divided by negative 32. Hit the green button before you hit enter. I'm getting 12.7225. It's a really long time for something to hit the ground. Okay, now a question you might be interested in is how fast is that ball going when it hits the ground, right? Because you may want to know about the impact, like the force of impact there. So if we want to know velocity when the ball hits the ground, what should we do then? Plug that time into our velocity formula, right? So v of 12.7225 is going to equal negative 32 times 12.7225 minus 10. So negative 32 times that number minus 10. I'm getting negative 417.119. And that would be feet per second because it is velocity. Yes. Thanks for the reminder, though. Forget too often. All right. Okay, questions? All right. Okay, so on the moon, we have a different situation because we don't use the same formula on the moon because the gravity is different. So in 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these fallen objects is given by this equation here, where S is the height in meters and T is the time in seconds. What is the ratio of Earth's gravitational force to the moon's there? Is this feet? No, this is meters and seconds. So, this gives position, right? So I think we want to compare acceleration due to gravity. I might have to watch Mr. Record's video. I'm pretty sure that that's what it's on here. So if we've got position here, if we want to know velocity for that object, we would do, actually, let's S prime of t would give us the velocity, which would be, we would multiply here, so we would get negative 1.62, right? 1.62t. And then when we take that derivative of our velocity, v prime of t is going to give us acceleration. We would get just negative 1.62. And this is meters per second squared. So we don't want to compare this with example 2, because example 2, how are we measuring that? Feet. This one is in meters. So physics, children, acceleration due to gravity on Earth is 9.8 meters per second squared. So it wants the ratio of Earth's gravitational force to the moon's. So Earth is first, so it'd be negative 9.8 over negative 1.62. And if we do that, we get 6.4 or 6.049. So there's about 6 times more gravity on Earth than there is the moon. Okay, questions? All right, we've got one more we're going to do here. All right, we want the second derivative of cosecant of t. Okay, so y prime of t is what we need to find first. And what is our derivative of cosecant of t? That one's one I bet we don't have memorized very well. I think it's negative, isn't it? Negative cosecant t cotangent t. All right, not so bad on first derivative. Second derivative, Okay? What have we got to use to take the second derivative? Product rule. So we're going to have negative cosecant t times the derivative of cotangent. What is our derivative of cotangent? I think it's negative cosecant squared t. Isn't it? Somebody got that out. I don't use them very often either. Plus cotangent t times the derivative of negative cosecant t. So that's going to be cosecant is going to be, it's negative, but there's also already a negative there, so it's going to be positive cosecant t cotangent t. So we are going to get cosecant cubed t plus cosecant cotangent squared t. Should have a t right there. All right, now this is our second derivative response. Stop here. But they're probably going to simplify that some. So what could I do here? I could, but there's going to be an easier way to deal with it. I've got a cosecant right here that isn't in both, so I'm going to factor out a cosecant t. So that'll leave me with cosecant squared t plus cotangent squared t. Now, when we did trig identities long ago, the Pythagorean identity was sine squared, we'll use a t since this is t, plus cosine squared t equals 1. Everybody always remembers that one usually. Okay, underneath that on the quiz there were two more. One of them was for tangents and secants, the other was for cotangents and cosecants, right? You might remember them without looking. I'm thinking we probably don't remember it. But let me show you how to get there, because honestly, I have to stop and think this way too. I am not the best at memorizing things. But if I can remember the logic behind it, I can come up with it. So, if I'm wanting to get cosecant, cotangent, look what happens if I divide by sine squared for everything. Right, that's a legal move right there. Sine over sine is going to be 1. Cosine squared over sine squared is cotangent squared. And this is going to be cosecant squared. So, if I want to switch this all to cosecants or all to cotangents, probably, because I factored out that cosecant, it'd probably be better to switch everything to cosecants, I'm thinking. So, if I subtracted 1 right here, cotangent squared t equals cosecant squared t minus 1. So I could use that because I know that sine squared t plus cosine squared t is 1, and I have just sort of rearranged that formula. This is still Pythagorean identity. It is true. So if I have a cotangent squared t, I can replace it with cosecant squared t minus 1. So I would have cosecant t, cosecant squared t plus cosecant squared t minus 1. And that would give me cosecant t times 2 cosecant squared t minus 1. And they may leave it factored. They may distribute that back out. There's several ways they could leave that, but I think that is as far as we can go for that. Now, if it were free response, you could stop right there. You wouldn't need to necessarily do anything else. Okay, questions? All right, so that's all we have on the notes. Your assignment, let me close this out. Our plan tomorrow is to review. So I have a test review that we're going to do in class. It is going to take most of the class period. Okay. The progress check is also going to be assigned. It is just the multiple choice part. Since hopefully you're going to get this done right now, I would try to do this tonight to not be overloaded studying for your tests there. So that would be my suggestion on that. So it is on AP Classroom. I think there's only one section for the multiple choice, and I think it's like it's either 15 or 18 questions, I believe. The FRQ assignment I gave you for this week is the progress check. So you're going to do it, but you don't have to do it on AP Classroom. You're just going to do it. And it's not due until Friday, but it would be great if you could look at it before. It is worked into this review that we're going to do as well. So it would be great if you could look at it before we have our test Thursday.